Hi guys, I'm doing this video so that we can talk about the product rule for derivatives. And the challenge is to find a rule that expresses the derivative of f times g. And the reason that this is a challenge is that the natural conjecture might be that the derivative of a product equals the product of the derivatives. This turns out to be wrong. And here's a counterexample. If I look at the derivative of x squared, then you already know from the power rule that the derivative of x squared is equal to 2x. But if I were to write it as the derivative of x times x and try to use my conjecture would tell me that that should be equal to 1 times 1, which is not the same as 2x. And so this means that the product of the two derivatives here is different than the derivative of the product there. This conjecture turns out to be false. So what is the derivative of f times g? I'm going to develop this in a manner similar to what Leibniz did. And I'm going to do it by visualizing what it means to multiply f times g. And usually mathematicians envision multiplication as computing some kind of an area. So if you imagine that I have a rectangle whose length is f of x and whose width is g of x, what we're going to do is to let x change by a little bit, and we're going to observe how the area, which is equal to f times g, changes when x changes. So let's let f change by a little bit, df, right here. And let's also let the width g change by a little bit, dg, right here. So that when f and g change, what I end up with is now a new rectangle whose area, in this case, is a little bit larger. So that the old area of x is equal to f times g. And the new area of x plus h, when x changes by a little bit, is equal to f of x plus h times g of x plus h, which is equal to f of x plus df times g of x plus df dg also. In other words, changing x by h leads to a change in f df, and it leads to a change in g dg, and that leads to a new area right here. All right? Well, we can find the new area, the extra added area, either from geometry or from algebra. If I find it from geometry, then I observe that the extra area that I added has three different components to it. It has this rectangle right here, whose area is width f, it's going to be length f times width dg. So the area of this little piece right here is f times dg. Meanwhile, the area of this piece right here is g times df. And finally, the area of the little corner down over here, which nobody really cares about much, is df times dg. I could actually get the same thing algebraically by simply multiplying out my expression right here. If I multiply this out, what I get is f g for the first term, plus df times g, or g df, for the next term, plus f dg, plus df plus dg. And if you look at each of the four four terms right here, you can see that each one of them is represented by a different rectangle up in the original diagram. The FG is the original area, and the GDF is the rectangle right here, and the FDG is the rectangle right here, and the little tiny DFDG is the rectangle right here. Okay? What Leibniz does is he subtracts the original area to get A of x plus h minus A of x. He subtracts A of x from both sides, and this he calls dA. It is the change in A that is caused when x changes by h. And according to our algebra here, that is equal to g df plus f dg plus df times dg. Now here's where Leibniz reasons. He says, let's divide through by dx to get a rate of change. And when he divides through by dx to get a rate of change, then in the first term, he gets a perfectly respectable result, which is g times f prime. And in the second case, he gets a perfectly respectable result, which is f times g prime. And Leibniz argues that when I take a little tiny piece df and I multiply it by a little tiny piece dg, the limit as dx goes to 0, this thing is going to vanish. So that what you end up with is a negligible amount of change for that third rectangle. And if you take a look at that third rectangle, you can see that the amount of area here added is practically 0 compared to the large areas added here and here. And as df and dg both shrink to 0, you can see that's really true. So that what we end up with, what Leibniz ends up with, is a derivative rule, which is the derivative for the area, or the rate of change of fg, which is equal to g of x times f prime of x plus f of x times g of x. Now what I've done here in this video is to appeal for our product rule, do some geometry, and to do a little bit of hand waving with these small pieces df and dg. Tomorrow we're going to do a formal proof with using the limit definition, and we're going to see that this is exactly the correct result. But for now we want a slogan. Observe that when we do our product rule, what we get is the first function f times the derivative of the second, plus the second function g times the derivative of the first. So our slogan for the product rule is first times the derivative of the second, plus second times the derivative of the first. Fg prime plus gf prime. Now let's see how this actually works out in practice. Take a look at the derivative of 2x plus 3 times x minus 5. What I observe here is that I have two different functions multiplied by each other. And so I can now appeal to the product rule by identifying the first function as the f and the second function as the g. And so the product rule gives me that this derivative is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. hard to use, the only thing that's going to be hard is to still that urge to try to just take derivatives and multiply them. Don't do that, you'll get the wrong answer every time. And now we can carry on and consider each derivative separately. Here we have a linear function whose derivative is the slope 1. And over here we have a linear function whose derivative is the slope, which is 2. Putting it all together, we get 2x plus 3 plus 2x minus 5 minus 10. Excuse me. My failure to distribute. And this adds up to 4x minus 7. Now, remembering the previous night's homework, some of you may say, couldn't I have done some algebra first to simplify this? Yes. So an alternative approach could have been to multiply through, and when I multiply through using FOIL, what I get is 2x squared. That would be plus 3x minus 10x is minus 7x, and minus 3 times 5 is 15. And if I go through and term at a time differentiate, I get, again, 4x minus 7, which agrees with what I got from the product rule. Which one was easier in this case? Well, in this case, it was easier to multiply through and then differentiate. It's nice that we got the same answer as the product rule, but the product rule seemed a little cumbersome. But there are circumstances in which the product rule is either easier to use or is going to be really our only option. Consider the derivative of x times the square root of x. Here I again have a product where my f of x is x and my g of x is the square root of x. I don't have the option of simplifying this with algebra because I don't have any way to deal with the result that I would get. So I can appeal to the product rule and say that this is equal to the first times the derivative of the second, plus the second times the derivative of the first. And I have derivative rules for each one of these. The derivative of the square root of x is 1 over 2 roots x. And the derivative of x is 1. Now this can be simplified a little bit because I have x to the first divided by 2x to the 1/2. And subtracting exponents, this gives me x to the 1/2 over 2 plus x to the 1/2, which is the same as x to the 1/2 times 1/2 plus 1. So this can be simplified to here, but of course this would be a perfectly good answer also. So I hope this is helpful to you.